Good morning, my fellow mathematicians. I'm Chance. I'm here to do theorem 21 for you for real analysis, which states if f is continuous on the closed interval a comma b, and L is a horizontal line, a comma f of a is below L, and b comma f of b is above L, there exists a point x in the closed interval a comma b such that x comma f of x intersects L, or x comma f of x lies on L. Now, theorems needed are axiom 4, which is if a is less than b, a plus c is less than b plus c. Theorem 20, which is if f is continuous on the closed interval a comma b, and f of a is less than 0 is less than f of b, then there exists x, that's an element of the closed interval a comma b, such that f of x equals 0. So, here we go. Proof. Let L be a horizontal line, and let alpha be the height of L, such that for all elements of L is at height alpha. Or L is defined as the line y equals alpha. Let f be continuous, and let f of a be less than alpha, and f of b be greater than alpha. Let x be a point on the closed interval a comma b, and f of x be an element on the closed interval f of a comma f of b. Case 1, alpha equals 0. If alpha equals 0, then the line L is at 0, and there is a point on the line 0 at which the closed interval a comma b will intersect, because a is less than 0 and b is greater than 0 by how we defined our alpha and f of a and f of b. And I meant f of a is less than 0, f of b is less than 0. Not an a and b. So there exists x comma f of x, which equals x comma alpha, which lies on L. And that is shown in this picture right here. And now, case 2. Alpha is not equal to 0. Then what we can do is subtract alpha from every range element. So we have L minus alpha equals 0. Then we have x comma f of x minus alpha, a comma f of a minus alpha, and b comma f of b minus alpha. And by axiom 4, all of our inequalities hold, and we're defining g at g of n to be f of n minus alpha for all n in the elements of the reals. Then g of a is less than 0 is less than g of b. Therefore, by axiom 20, there exists x comma g of x, that's an element of L minus alpha, meaning x comma g of x intersects L minus alpha at 0. So now we can add alpha to everything. And if we add alpha to x comma g of x, we get x comma f of x. And since that's at the point 0, 0 plus alpha is equal to alpha. Therefore, we get that the point x comma f of x is an element of L, because L is the height of alpha. And this is just a fancy way of saying all that. And since alpha does not equal 0, and based on how we set it up, we don't have to do two cases for alpha being greater than 0 and alpha being less than 0, because if alpha is less than 0, then you subtract it. You're subtracting a negative number, which gets you closer to from a negative number, which gets you closer to 0. So there's that. Here's the picture for case 2, which is where we have this function at alpha is not equal to 0 at L, and that's a comma f of a, b comma f of b, and that's x comma f of x. And that's a function without a line, basically saying we're going to have it mapped to g, and it's basically going to be the same thing as this. Then we're just adding it to get it back up to the L value. Alright, bye!